Picture a supercar built for 300 miles an hour stuck bumper to bumper in rush hour traffic. That's your CPU. A modern processor can switch billions of times a second, 5-6 gigahertz of raw speed. Its memory can't keep up, not even close. There's a name for this gap, and once you see it, you can't unsee it: the memory wall. Some of this is pure physics. Every centimeter of copper between the CPU die and a memory module costs time. Even at the speed of light, that's a real, measurable delay. But distance is only half the story. Even memory sitting right next door still has to physically charge and read its own internal cells, and that takes longer than any wire ever could. The result: a control unit with billions of transistors ready to fire sitting completely idle. Engineers have a word for it: starvation. Every instruction your CPU runs moves through the same three-stage line: fetch, decode, execute. Decode and execute are lightning fast, pure logic, no waiting around. Fetch is the slow one. It's the factory worker standing still, watching for a delivery truck that hasn't shown up yet. Here's exactly where it breaks down. The program counter has one job: point to the address of the next instruction. It does that instantly, but pointing at an address isn't the same as having the data. Between here's the address and here's the value, there can be a gap of hundreds of cycles, the CPU doing zero useful work through every single one of them. This isn't a bug. It's the architecture almost every computer still runs on. Separating memory from the processor means everything, every instruction, every byte crosses the same narrow highway to reach the CPU. For 70 years, transistor counts have exploded. That's Moore's law. Memory access times have barely moved. That growing gap has a name: the memory wall, and it's been widening for decades. You'd think more cores would fix this. They don't. Every extra core is another car merging onto that same narrow highway, all competing for the same memory bandwidth. More compute power funneled through the exact same choke point. So chip designers fight back with prediction. Branch predictors guess which way your code is about to turn, so the pipeline never sits idle waiting to find out. Prefetchers do something different. They guess which data you'll need next and go fetch it before you even ask. Both are educated guesses. Both are wrong often enough to matter. The other defense is cache: L1, L2, L3, small pools of fast memory sitting closer and closer to the core, like emergency stockpiles. Most of the time it works. But feed a CPU a massive, unpredictable dataset, and those stockpiles run dry. That's a asterisk cache miss asterisk. And when it happens, the CPU doesn't wait a few cycles. It drops everything and waits hundreds of cycles for a full round trip to main memory. So the industry's best fix right now is simple in concept. Move the data physically closer to the compute. AMD's 3D V-Cache already stacks extra cache directly on top of the CPU die. And it's still scaling, with next-gen chips reportedly pushing toward hundreds of megabytes stacked in 3D. Pause on the memory side. HBM4 high-bandwidth memory entered mass production in 2026, doubling the interface width of its predecessor to feed data-hungry chips faster than ever. But researchers are chasing something more radical: compute in memory. Instead of moving data to the processor, what if the memory itself could compute? Early chips already do this, still mostly in labs, not on your desk yet, but the direction is clear. Here's the takeaway. For decades, we optimized software to reduce calculations. In 2026, the real cost isn't the math anymore. It's the distance the data has to travel to reach it.